Okay, welcome back. Now we're going to look at the main hydration peak. So in the last module, we looked at the induction period, how that this is not related to protective membranes, it's just related to undersaturation and dissolution theory. And now in this module, we're going to look at this main hydration peak. That's to say, the period between about 3 hours and 24 hours, in which we have first this very strong acceleration in the rate of reaction and then this deceleration. And the main question that's really posed in this period is, why do we go from this acceleration? Why doesn't it just continue accelerating to the deceleration? Because the amount of reaction at the peak here is still relatively modest. So in terms of what's happening in acceleration, I think the situation is quite clear, that here we're looking at the nucleation and then the growth of CSH. So on these slides, we can quite see at about 2 hours, we can see these little tiny nuclei of the CSH which are forming, and then those nuclei grow over time. And as they grow over time, they grow in this, what we often call a kind of needle morphology, where it looks a little bit like a sea urchin. Now, I'm going to use the term needles, but depending on the different conditions, sometimes they can look more like foils. Even here, we can imagine those needles are actually tapered foils. So, don't worry too much about those differences. We can find quite a lot of variation, but it's all this kind of outward growth. People have been studying nucleation and growth for a long time. These images here summarize the theory of Avrami, and Avrami was one of the first people to really quantify these processes. And what Avrami was doing, he was studying solidifying metals. And in solidifying metals, you have a liquid, and then these nuclei, represented in here, form, and then they grow. And the rate of growth is proportional to their surface. So as, first of all, they get bigger, the growth rate goes up. And then as these nuclei grow into each other, you can see the surface available for growth goes down. So you get this deceleration. So he analyzed this process in quite some detail, came up with some very powerful equations, and this just shows a couple of his equations. And because this kind of form of reaction where we have this peak, this looks rather similar to what we got in cement paste, for about 50 odd years, people have been trying to say, well, can we apply this quantitative analysis to cement paste? And indeed, because it's such a simple shape, you can quite easily fit this to cement hydration. But the problem is that then you come up with parameters that have no physical meaning and vary enormously from one cement to another. So this really underlines the fact that to really understand the right mechanism, you have to do a very wide range of experiments and you have to analyze those quantitatively. Now, in terms of doing the quantitative analysis, it's very useful to be able to rely on computer models. And one aspect which we need to well capture in computer models is the fact that we have a very wide range of particle sizes. We have some cement particles that are about 60 microns in size, some are less than a micron in size. And this means that in a typical box, so this would be a typical box of 100 microns, we may have many millions of particles. And this shot here shows the model we call Mike. Mike is this a model developed at EPFL by Shashank Bishnoi, and it has this cute little logo. It's written like this, but that's because it's Mike for microstructure. Okay, so we could use this modeling platform to test different hypotheses. So the first hypothesis we tested was this classical idea, sometimes called boundary nucleation and growth, where we have our surface, which is A-light, we have the CSH growing on the surface, and the growth rate is proportional to the surface of the CSH, so that eventually growth will slow down when material from one grain impinges with the other. If we look at the results from this, and what's quite important in these results I'm going to show you is that we tested this on a range of particle sizes from the same A-light. So these numbers here tells you the average particle size of the different A-light, but in fact we had the whole particle size distribution which we could simulate in the model. And what you can see here is that in this modeling we can capture very well this acceleratory period, but after the peak we get a very poor correspondence between what the model shows and what the experimental results is. Basically, we don't get the deceleration. And if we look at the screenshot of the model at the peak, you can see here there's a very small amount of product, so it's not surprising we're not getting much impingement between the product. So what can be an alternative? Well, classically, many researchers have proposed that what happens at the peak is that we switch the mechanism. We go from a nucleation and growth controlled mechanism to a diffusion controlled mechanism. And the idea is that we have our cement grain here, we have our solution out here, we have our product layer in between, and that either the water has to diffuse in or the products have to diffuse out. And probably both, but we don't know which one is rate limiting. So that's, again, seems quite a nice hypothesis. It's a hypothesis that fits very well in a number of other reaction studies. And we can use our modeling platform to look at that. And here we see the results. And at first glance, this looks okay, because you see the model now fits fairly well with the experimental results. But, and this is a very important, but because we did these simulations on this wide range of different particle sizes, and we see that to get them all to fit, we've got to vary our diffusion coefficient by 10 times. Now, this makes absolutely no sense whatsoever, because this is exactly the same A-light, we're forming exactly the same CSH, and there's absolutely no reason that this diffusion coefficient of that CSH should change by an order of magnitude. Clearly what this shows is, you can make a lot of mechanisms fit, but you have to go further to really see what can be the right theory. So we really have to abandon this idea of diffusion, and there are a number of other reasons why we should do this. So here we have the first reason I showed you in the last slide, that there's no reason why this diffusion coefficient should change by an order of magnitude. But also, those of you who have perhaps looked at different ways of calculating maturity will be familiar with the idea that we can use a single activation energy throughout that main hydration peak. And we wouldn't expect that if we had a transition in mechanism. So if we went from a mechanism which is like nucleation and growth, which is to do with bond breaking and making, this would have a typical activation energy around 40 kilojoules per mole, which is typically of the same order of what we find in cement paste, whereas transport controlled processes such as diffusion have much lower activation energies, less than around 20 kilojoules per mole. So there's no evidence from this activation energy. And thirdly, if we look at a micrograph, this is taken at 1 day, so we're well past the heat peak here. And what we can see, this is our A-light grain on the right here. This is our CSH forming. We have got this kind of shell here, but we really cannot in any way defend that this shell is acting as a diffusion barrier. Because if this shell was acting as a diffusion barrier, we would not expect to see this region of low density behind the shell. We would expect this to be right in contact with our A-light grain. So these many reasons really are evidence that diffusion is not becoming the rate determining mechanism at this stage of the reaction. Then, with the work with Shashank Bishnoi, we really looked at this formation of product, and this formation of product, you can see it's not really all that uniform. That's to say that the kind of average density out here is quite a bit less than the density close to the particles. And so we put forward a new hypothesis that CSH was first forming in a low density way and then subsequently densifying. And because it's got this low density, then it can occupy more space, and you can imagine to have impingement between the hydrates much earlier than you would otherwise expect. And this theory was developed quite rigorously and quantitatively, and we see from these results here that it really appears to work very well. And in 2009, we published this paper where we put forward this hypothesis. Unfortunately, as is often the case in science, we then come to a counterexample, which really shows that this new theory was not right either. The critical experiment is this one, which we did with Amélie Bazzoni, but has also been done by a number of other people, where you can see we have a very different water-cement ratio. So here we have hydration at a water-cement ratio of 0.4 and 0.8. According to this densifying growth theory, we would expect for the water-cement ratio 0.8 there to be a lot more space, and therefore to have a lot more hydration before this downturn. But in fact, we don't see this. We see just a little bit more hydration before we get this downturn. So unfortunately, we have to abandon this new hypothesis. Also, in the thesis of Amélie Bazzoni, we had another source of alite, which gave us a different perspective on this question. And this was really where we had alites, which on the one hand contain small amounts of zinc, and on the other hand, small amounts of magnesium. So we had the pure system, magnesium, and zinc. And what you can see in the calorimetry curves here, that the presence of low amounts of zinc gives you this vast increase in the amount of hydration that's occurring in this first heat evolution peak. So there must be something different that's occurring with the zinc dope sample, which is telling us about what's controlling this main heat evolution peak. So when we made the more detailed investigation by transmission electron microscopy, what in fact we see here, we see these needles that are growing out from the C3S surface are much longer in the case of zinc than in the case of magnesium and the pure case. And we could quantify that. So here we see the quantification of the needle's length. We don't know exactly the mechanism, but we could see that the zinc is really incorporated into this CSH, whereas the magnesium is not really being incorporated at all. It's just occurring as these little isolated crystals. So this gave us a new hypothesis, another new hypothesis, that the idea is we get this CSH growth in needles on the surface of the grain. By the time you get to the peak, the surface is covered, so no more needles can grow. And as no more needles can grow, the rate of hydration starts slowing down, and you get the formation of inner product. But as I've already said, the critical test of any hypothesis is whether it works quantitatively. And for this, we're now working on a new model, which is called the needle model, which has been worked on by Alexandra Uzier in our lab at the minute. And this hypothesis is we have CSH growth as needles. What's very, very important is that all the parameters can now come to the experiment. There's no fitting in what I'm going to show you here. And because it's an algorithmic model rather than a computer model, a model that works in terms of having a real microstructure, we can also calculate much more complex form for the grains and take account of the consumption of the small grains. And when we do that, you can see now in these different simulations, this really works beautifully throughout the whole range of different variations we've already seen. It can really well capture this water-cement ratio variation, and it can really well capture the effect of the zinc doping. So hopefully this is now the hypothesis which can be validated. Of course, we're not at the end of the road because there are important open questions. So if this mechanism is controlled by these needles that grow and then stop, What's controlling this? Unfortunately, today we can't answer that question, but with work we have underway looking at the much more atomistic level, I'm pretty confident we'll be able to answer this in a year or so's time. So let's come to the summary on this main peak. The first and foremost thing is that just because you can do a curve fitting, that doesn't mean the hypothesis is right. You can take many equations that have this simple form of a peak, and they look right. If you're going to differentiate between these different hypotheses, you need to look at hydration with a wide range of variables. You need to vary water-cement ratio, particle size distribution, look at the dopants. All these different things are really important to give you the range to test your hypothesis. And ideally, you need to have physically measurable parameters, because if you can do that and if you can avoid the fitting step, then you can really be much more confident that your hypothesis is working. And having followed that process over the last few years, we're now fairly confident that we can explain this by this growth of needles to a critical length as being the best hypothesis for this main hydration peak.